thermal 15. How can we use the pH diagram and enthalpy to solve for the COP here? I know the cycle is different for a Carnot cycle. I spent some time on doing this with this method, but a discussion on this would be helpful to understand. So how can we use the pH diagram and enthalpy to solve for COP here? I think your question, if you're doing Carnot heat, you're doing Carnot COP, just like we talked about in the previous example, it's a function of temperatures. So you only really need the temperatures. So what does that have to do with the pH diagram? Well, let's remind ourselves what a heat pump cycle is going to look like on the pH diagram. Here's our refrigerant or gas, whatever you want to call it, because it's a heat pump cycle. But remember, a heat pump cycle is exactly the same as a refrigeration cycle. It's just that the thing that we care about in a heat pump cycle is different. In other words, we're going to number our states all the same: 1, 2, 3, 4. Compressor from 1 to 2, condenser from 2 to 3, expansion device from 3 to 4, and evaporator from 4 to 1. So the evaporator absorbs heat and the condenser rejects heat. In a refrigeration cycle, we care about the quantity of heat being absorbed as we go from 4 to 1. We care about the evaporator because our desired output is removing heat, performing cooling. In a heat pump, it's exactly the same cycle, but what we're interested in is the amount of heat that's rejected from 2 to 3 because we're trying to do heating. So, but anyway, we need to know the temperatures because the Carnot COP, as we wrote here, is a function of temperatures. So then the question becomes, what are the operating temperatures for this cycle? And in other words, we need to know T low and T high. Well, inside the vapor dome, the temperature is constant. So from 1 to 4, the temperature isn't changing. It's just phase change at a particular temperature. So if you wanted to look up the pH diagram for that particular refrigerant in that problem, you could do that if that diagram is available in the reference handbook. And then you would say TL is equal to T1, or you could also say T4 or anything in between because it's just a horizontal line, and that's a line of constant temperature. Now, 2 to 3 is a little bit different because the temperature at 2 is greater than it is everywhere from 3 to this point right here when we start to go out into the superheated region. But in terms of defining the high temperature, we should use what's inside the vapor dome because the amount of sensible heat transfer that happens from 2 to this location here on the right side when we go into the superheated region is negligible, and the big story is what happens inside the vapor dome, where there's actually phase change. That's really where the magic's happening. So TH, we'll define it as T3. So if you wanted to go away and do that graphically on the pH diagram, you could grab these two temperatures that way and then proceed with the COP for a Carnot heat pump using this formula. And that's what we did in the solution video, so you're welcome to go back and rewatch that. You can also use the table right below that refrigerant's pH diagram, and that'll give you the same values as well. And do remember, just as we talked about in your last question, you do have to change these to absolute temps. It's very important. I'll reinforce that one.